So good morning, everyone. Thank you all for being here. So I'm Sébastien Crozet, and today we will be talking about GPU scientific computing in Rust. So a little bit of introduction first. I started working with Rust quite a few years ago, more than 10 years now, because it was before the very first version of Rust. And one of the very first crates I've been writing is the nalgebra crate, which is a linear algebra library. And then I've done quite a few work for scientific computing with geometry, physics simulation, with encoded and physics. And more recently, I've been working on Rapier and Rapier, also for rigid body physics simulation. But all of that is running on the CPU. And more recently, I've been wondering, okay, what can I do on the GPU? And the realization here is that GPU scientific computing is very difficult. Like, it's a completely different story compared to CPU. And there are a lot of challenges which are not only unsolved on the Rust ecosystem, but also on any GPU ecosystem in general, which is that, okay, because GPU scientific computing is hard, you already have a very small number of people working on that. So if you are looking for code to reuse, you don't have that many options, and you also don't have the tools to reuse these easily. Like, for example, if I'm doing physics simulation, one of the very first features I need would be some linear algebra and maybe some quaternions implementation. So if I am working on the CPU with Rust and I need a quaternion implementation, what I would do is just look into crates.io and find a linear algebra library, maybe like an algebra, and add dependency to my project. And that's it. I can just reuse the code immediately. But for GPU, it's not the same story. We don't really have any kind of package manager for GPU code. So you would maybe find an implementation, copy paste the code into your own code base, and somehow make it work. So it's a bit tricky. The modularity story, it's basically non-existent. And the second thing too is that today, scientific computing is very much dominated by CUDA, at least on the field I've been working on. So in physics simulation, if you open a paper, you will most likely see that if it's about GPU computing, it will be based on CUDA. And this is for very good reasons, because CUDA has a very good ecosystem. NVIDIA does provide very strong libraries like QBlast, so it does make sense. But now the problem is that this is based on proprietary technologies. So what I would want is something like Rust, which is I write my code once and it runs just everywhere. So how can we open this to every platform, and how can we solve this modularity problem? So I think I got a little bit lucky here, because there is one solution which is at the same time a bit old and also a bit new, because it's old since it has been developed by NVIDIA for a few years now. But it's also new because it got donated to Khronos at the end of 2024. And since that donation to Khronos, Slang started having a lot more interest in the open source community. So what is Slang? So as you can see here, Slang is at the same time a shading language for the GPU, as well as a compiler for that shading language. So on the left-hand side here, you can see the inputs. So it's the Slang shading language, but also HLSL and GLSL, but these are mostly for compatibility with existing code bases. What you really want to do if you are writing new code is to write your code in Slang directly. So you give these shaders as input to the Slang compiler, and what it will do is convert all of these into your platform-specific shading language. So if you are targeting Metal for macOS, it will generate an MSL shader. If you target the web, you will have a WGSL shader. For CUDA, you will have a PTX file, etc., etc. So you can see it has a very, very wide support of different platforms. And in a way, at least in the Rust community, this can feel like a superset of what we have with WebGPU, NAGA, and WGPU. So this is amazing. But in a way, you might be thinking something like this meme from ESKCD, which is we started with N competing shading languages. So, of course, we want to unify everything. We want to make something universal. And we just end up with N+1 shading languages. So I don't know if this is what will happen, but what I do know right now is that today Slang does solve the issues I've been having, which is that it is completely open source, it is open governance, thanks to the Khronos initiative. I do write my code one time, and it works on every platform. Now, of course, it doesn't mean that if it's efficient in one platform, it will be efficient on every platform the same way, but you do have the ability, if you want, to make some platform-specific optimizations afterward. So it really works well with incremental development and also with community development, because contributors can start contributing a shader and iteratively make it better for X or Y platforms. It supports both compute and rendering. So it means that you can reuse the same shader code bases for compute and rendering, which I think is very great. Like if I do physics simulation, the next step is, of course, rendering that physics simulation. So I do want to reuse the same types. I want to reuse the same buffers, etc. So that works very well with Slang. Unlike the web GPU standard, we are not limited with like the weakest platform we want to support, because Slang will allow you to write code to use features from platforms, from any platform you might want. And if you are targeting another platform which does not support it, it will just not compile. So you can have some conditional statements which say, okay, for that, if I'm targeting CUDA, for example, I will be using floating point atomics, but if I'm targeting web GPU, then I have this fallback I can use. Slang has a very interesting feature that I haven't been trying yet, which is automatic differentiation. But I do hope this will allow me at some point to write a differentiable GPU-based physics engine, but we'll see. Slang has a very modern syntax, so if you are used to writing WGSL code, you will see that it's really refreshing to write Slang. We will see just a very small example afterward, and yeah, it's really, for the first time, is a good GPU language to use. Reflection. So reflection is the ability for you to query the Slang compiler for informations about the Slang shaders you are compiling. So the key element here, I think, is that if you are familiar with dealing with rendering GPU shading languages, is that you have to always deal with these binding groups and binding indices. And this is a mess to work with, especially if you start to combine multiple modules which have their own definitions of some buffers with some bindings. You have to make sure you don't have any overlap between them. It's a mess. Thankfully, Slang does this allocation of indices for you, and you can just ask the compiler, okay, this input for that kernel, tell me which binding group and which binding index I need to use. It has nice tooling, so I'm using Rust Rover, so I don't really benefit from that. But if you're using VS Code, it has a very, very good IntelliSense feature. and it will have integration with Nsight and RenderDoc. And overall, it's just very fun to work with. It's kind of like when I started with Rust, like it was very new. The community was still pretty small. Everything needed to be created, and it kind of feels like the same here. Okay, there is this small QR code here, which I really recommend watching. So it's about a 1 hour long video from Khronos. And in that video, which is from SIGGRAPH 2025, they are describing a bit more about how Slang works, what's the roadmap for Slang, like the new features they are working on, etc., and a few examples of use cases. All right, so Slang, everything I've told until now is about shaders. Now the question is, how do you actually use these shaders in Rust? And to explain that, I will be comparing with the web GPU ecosystem, because in Rust, you can work very easily with web GPU. So you need 4 components, or at least for web GPU, you need 3 components. The first is the shader compiler. So that compiler will do what I showed earlier, which is it will convert from your shading language, which for web GPU is WGSL, into your platform-specific language, which would be Metal, like MSL, HLSL, etc. So for web GPU, that library is named Naga, and it's written in C++. It's written in Rust. So you don't need any kind of Rust bindings to use it from your project. So next, you need an RHI, which is a render hardware interface. So that one is about being able to communicate with your GPU without actually knowing what's the actual backend you are using. So, for example, you will write create buffer, and WGPU will know if it has to call the create buffer function from Vulkan or from Metal, etc. So you write your CPU code once for communicating with the GPU, and it will work on every platform. And finally, and that's the part I find more interesting, you get to write your shaders, your mathematical shaders. So last year, I started working on this project, which is called WGMath, which was about creating this scientific computing ecosystem for web GPU. So it had some features like some linear algebra features, like the kind you find in nalgebra. It also has some geometry, some physics, and some AI, but now I have switched to Slang. So let's see what it looks like with Slang, and it's about the same thing. So we also have a shader compiler, which here is Slang. Slang is written in C++, so you do need some bindings to call it from Rust. And thankfully, when I started with this work, bindings already existed. So we had like the shader Slang library already existed, and it actually works very well. So it does cover everything you need for compilation, and it also supports the reflection API of the Slang compiler. Now, everything in green did not exist. So this is what I've been working on. And I only started this like 3 months ago, so do expect that it's very experimental. Future version will probably have some significant breaking changes, and they do lack some features. So it's more like in the proof of concept stage rather than a proper release. So mini Slang is just a small wrapper around shader Slang to make some things easier to use. In particular, we will see with just 2 or 3 lines of code, you can check if your Slang shaders compile at compile time. So when you write cargo build, it will check if the Slang shader compile, and if they don't, you will get your compilation errors. Next step is the RHI. So with Slang HAL, it's basically the same goal as WGPU, but for Slang. So right now, because I am mostly focusing on compute, Slang HAL only supports compute shaders, and it will, for now, only support the web GPU backend and the CUDA backend. So I picked these two because I had some experience with web GPU, and CUDA because it's so different from web GPU, so it really shows the versatility of the system. And finally, the actual mathematical part, which are the reusable shaders. So there are a few libraries here, again, still very early in development. So S-Tensor, which is Slang Tensor, is a tensor library for Slang. So it provides the definition of tensors, operations like matrix multiplication, computing the sum of two tensors, the difference, etc. It also exposes some low-dimensional geometric operations like singular value decompositions, isometry, similarities, etc. So in general, the goal here is to become an algebra, but on the GPU. Nexus, that one is almost empty right now. So it only contains a few operators which are used by Slosh. But the goal of Nexus will be to be a GPU-based physics engine, rigid body physics engine. Slosh, that one is also a physics engine, but using the material point method. So this is a method for simulating non-rigid materials, so things like sand, water, etc. And finally, SLAY, which stands for Slang AI. That one is an LLM inference library. Okay, so we've seen a few different libraries. So now, how do you actually code anything with Slang and Rust? So we can start with the very typical basic shader, which computes the sum of two vectors here. And you can already see some very neat Slang features. And the first one might look kind of obvious, which is that you can specify here A and B, all these buffer arguments, as arguments of your actual kernel function. And this might feel very basic, like coming from a CPU world, but a lot of GPU shading languages, especially the render-oriented shading languages, actually take these arguments as global variables. So here, by having them here, it's much cleaner. You know immediately what your kernel takes as input. And as you can see, I don't have to specify any kind of binding groups, binding indices. So we have two buffers here. The first one is read-write access, and the second one is read-only. We have the identifier for the current thread. We check that it's not out of bounds, and we compute the sum. So we needed the read-write access for A because we are storing the result into A directly. So we say it's a compute shader with 64 threads for each work group. All right, so that one is fairly straightforward. So this is the Slang shader. So this is what will be converted to WGSL, to MSL, etc., etc. Now, from Rust, Slang HAL has some high-level features, including some procedural macros here. So on the Rust side, you will define a structure, which here it can have any name you want. So here it's named GPU add, and it has one field, which is add assign, which does match exactly the name of this compute shader here, add assign. So that one is a GPU function, and it's all parameterized by the backend. So you don't know what the backend is, but it does depend on the backend. Here, with this procedural macro, we can say, okay, this structure matches that module from Slang. So that module was the add.slang file, and we have the relationship here. So what this procedural macro does is that it will automatically generate for you some boilerplate code to identify the location of your Slang module and to compile that Slang module and to initialize the compute pipeline for add assign. All right, so then we need to write some code for actually telling the GPU, okay, now you need to run this shader, this compute pipeline with these inputs. I do hope eventually that I could generate all of this automatically, but right now it does have to be written manually. So you will define your arguments. So I have this structure here. At ours, it takes two buffers, one A and one B, and these two will match your inputs from your kernel here. And so you have that on one hand, and on the other hand, you have a launch function here that you can use to actually launch your pipeline. And you can see here that we still have this B type parameter everywhere, which is the backend type, but you don't need to know about which backend you are using to manipulate its buffer and to actually run the kernel here. So we are running the kernel with a number of threads equal to the length of A. And one other subtle note here, if you have been working with WGSL before, is that here we are specifying the number of threads, not the number of work groups. Like typically what you would do is divide that number by the 64 here. But here you don't need to. There is an option if you want to specify the number of work groups, but what's interesting here is that even if you change your shader and change that number to 128, for example, it will still work. And this is thanks to the reflection API of Slang, because the compiler is able to tell you what value exists on the shader so that you can so that Slang HIL can automatically deduce the number of workgroups based on the number of threads you want. So this is like, as a library author, this is all you need to write. Now, as a user of that library, you need to actually call all of this code. So you will initialize your buffers, you will create your shader. So that line here, GPU add from backend, this is generated, like the from backend function is generated by Slang HIL, and this is the one that will run the compilation using the Slang compiler. Then you launch the operation, and at the end you have a very small function which will read the data back from the GPU back into the CPU RAM, so you can do whatever you want with it. And finally, here, just for completeness, you have the main function where we actually create like the CPU side buffers. We just print the result. And at the very beginning here, you can see that we can select the backend. So here I'm doing this with a feature gate. So if you have the CUDA feature, then it will run with the CUDA backend. Otherwise, it will run with the web GPU backend. And you can see that switching between backend is just that. It's just depend on what value you have for this backend variable here. And that's it. Everything else works with a single way of writing your code. All right, so something optional, and this is something I mentioned at the beginning, is that using mini-Slang, you can write this line here, slang.compile all, and this one will just tell it, okay, I have that directory full of Slang files, read everything, compile everything, and give me an error message if something fails. And since I put this into a build.rs file, it will happen at compile time, which is, yeah, it's just extremely convenient. All right, So I have some demos with Slay and Slosh. Just before that, so I don't have to re-switch afterward. What's the next step of this project? Well, like I said, it's very early days, so it's basically everything. Everything needs to be done. The goal here was to really show that Slang can be usable from Rust. We can have a solution for writing shader once and have them work on every platform. And also something I haven't showcased here, but I can showcase very, very quickly is the modularity, which is that, for example, if I go into this code base, so very quickly you see all Slang shaders here, and I go into, I don't know, that shader, Softmax, you see that Slang supports import functions here. And that shader is actually imported from a different crate, so the S-tensor crate. So you can depend on a different Rust library and start using the shaders from that library to your own project. And so we have, like, Slang HA has a system to handle this, which essentially boils down to calling a registration function from your dependency. So it becomes just a single line of code. Yeah, if I go into the S-tensor library here, you see that I am embedding all my shaders into the compiled executable, and the shader registration just tells the compiler, okay, test, yeah. It just tells the compiler, okay, take these shaders and make these available for every other shaders. All right, so in terms of demos, I just wanted to show two things. So first, that one is Slosh. Choose the ones. So I am on battery, so it's about twice as slow as it should be if I was connected to the power. But that one is the NPM simulation library. So this is a bunch of sand with two-way coupling. Here it's one-way coupling with kinematic body originating from Rust, from test. Oh, sorry, it's glitching. So you have a few other demos here. This one is, so it's implementing the CPIC model for interaction with rigid objects. So you can have some very sharp cuts of elastic materials. And like about everything I do in terms of physics simulation, it works on 2D and 3D. And yeah, the second one is Slay, which is the LLM inference library. So right now it's only implementing two models. So Llama, Quen, and segment anything. So I can open a model here. Yeah, segment anything. So I open the model, just wait for it to load. I can select a picture for Angzu, so you can ignore this part. The chocolate cake thing is for the chat-based demo. But when I load this image, what it will do is it runs all the GPU operation for the image encoding, and then I have the image. I can click on it, and when I click, it will show you the result of the segment anything segmentation. So this is all running in Slang, and here this has been running on the web GPU backend. All right, that's about it for my presentation. So thank you all, and I really hope that we start getting more people using Slang in Rust. Thank you.
Thank you, Sébastien. 有没有提问题？我们可以有一个问题机会。你吗？你的优先级排后面。后面这个有位朋友来。哦 ，OK。
Okay, thank you for your presentation. I myself is a user of web GPU and WGPU, and I've also been quite interested in getting to know Slang. But one thing I see is that in Rust ecosystem, it's still pretty new, right? And one thing I'm quite curious is about how it's going to integrate with the rest of the ecosystem, because as you see, there are some crates like Bevy for game development, and there's also like Burn for machine learning. So I'm wondering, how long do you think Slang is going to start integrating with other crates, and what kind of direction is it going to be more focused on? Thank you.
Yeah, I think in terms of adoption by the community, I think the key part here is to have Slang HAL work well and with every platform. So basically, we would need something like WGPU but for Slang, so that it's really easy to integrate that into project. Now, I think the main limitation that might slow people down for the adoption of Slang is the fact that the compiler itself is written in C++ and not in Rust, compared to web GPU, where everything is written in Rust. So I think one of the key features which isn't implemented yet in Slang HL, which will help a lot with that, is the ability to link statically against the Slang compiler, so you don't have to deal with the C++ DLL. So as far as integrating into Bevy is concerned, I don't really know. It really depends on how Bevy feels about having this C++ based piece of code somewhere. But I think one area where Slang really shines is more on the compute side of things, because this is where web GPU really falls short. Like if you want to target CUDA right now with a single, the same sources as Vulkan or other platforms, you don't have any solutions. So there is some effort like kubectl, where you can write your shaders in Rust and compile it for different platforms, but this is a very different approach. Here you really write your shaders in Rust, so you do rely on the kind of magic that happens for compiling your Rust code into your backend specific code. I don't know, this can be very difficult to maintain in the long term. There has been in history some issues with the cust library for CUDA. So I don't really know how this will go. But in general, the key thing here is that Slang, like GPU computing is difficult. There isn't a large community. So with Slang, you can really have people from different communities and different languages contribute to these shaders. So you can have an ecosystem that is useful not only for Rust, but also for C++, and etc., because it's just a shading language, and the Slang developers themselves do hope to create a Slang package manager eventually.
Okay, thank you.
Okay, thank you, Sébastien. Thank you.